Hey team, this is your chemistry coach coming at you. You're ready for video number 11 for our acid-base series. I was going to put videos 10 and 11 together on polyprotic species and the problem, but they run pretty long because I really want to hit home those assumptions we're making and so you really understand them. So I figured I'd do the theory first in video 10 and then the actual problem in video 11. So here we go. This is something that is fair game, my friends, for your next exam and future quizzes, those types of things. All right, simple. Seems like a simple question. What is the pH of a 0.098 molar solution of H2SE? What is the hydroselenic acid, I think? Hydroselenic acid. And what are the equilibrium concentrations of all species? So remember, three things I can ask you mostly: pH of the solution, percent ionization, and equilibrium concentrations of all, any one or all the species. So I didn't ask for the percent ionization, but that's pretty easy. It's just X divided by the initial concentration of the acid. So we could easily have done that. How are we going to approach this? First thing we look at and go, oh no, there's two ionizable hydrogens there, two acidic hydrogens because they're out front. So this is going to happen in two steps. So if you freak out and your brain goes blip on a test, just write out the two ionization steps and then write out the equilibrium expressions and look up the Ka values and skip to the next problem. Maybe you'll let your subconscious work on it. But at least do that and get some partial credit if you don't remember how to solve the problem. Let's attack it. So let's go step one. We're going to take the original diprotic acid. Remember, we did H2A earlier, so A will just be selenium in this case. So let's take the H2SE, the hydroselenic acid. That's going to ionize with water. That is a weak species. So that's going to be popping its H plus over. You don't have to draw that little H plus coming over. Sometimes I like to show it. All right, so we're going to lose an H plus here. So this becomes HSE, and it was neutral and becomes negative. So that'll be HSE with a -1 charge. And then the water picks up an H plus. So that becomes the hydronium ion. We'll look up the Ka value for that in a second. So that's step one. So that'll be a Ka1. So if you have your Ka table, look that up for me right now and write that down. Let's do step two. Where's my purple pen? Here it is. So let's do step two, where this comes down. It has another acidic hydrogen. So let's do the next step of the ionizations here. So let's take HSE minus. And that can donate also its acidic hydrogen. Now that won't be very favorable because we're going to have a very low concentration of this conjugate base here. And it's got a very low Ka value, the Ka2 value you see when we look on the table. So hopefully that assumption we're going to make that this second ionization step is negligible. Hopefully that will work. And on a test, you know it should work. If it doesn't work, raise your hand and go, something's off here because you said this was supposed to work. And I'll be like, look here, fix that. Or I'll say, you should know how to do that. Let's finish this. The H plus comes over. Boom! Attaches to that oxygen atom there. And so we will lose the hydrogen and pick up another negative charge. So that will give us the selenide ion. Gosh, do you think I'm going to ask you for that? Yeah, I asked for the concentration of all species. So I'm going to want the concentration of this, the HSE minus, the hydronium ion, and the selenide ion. And we'll ask for all of those. And we need those tricks, right? So we're also going to get the hydronium ion there. And we can look up the second Ka value for this, Ka2. Let's get our trusty, dusty Ka table, or acid ionization constants. And this is hydroselenic acid. So take a look in alphabetical order. Keep going, keep going, keep going, keep going. Hydro, I'm trying to look upside down. Where are you, my friend? I think that's it right there. Hydroselenic acid, H2SE. All right, so Ka1 is 1.3 times 10 to minus 4. And then the HSE minus, the Ka2, is 1 times 10 to the minus 11th. Huge difference. That's like 7 orders of magnitude difference. That's wimpy. This is wimpy, but that's supremely wimpy. All right, so let me write those Ka values down. So so make sure you have this table and you're looking at what I do. The Ka1 is 1.3 times 10 to the minus 4. 1.3 times 10 to the minus 4. And Ka2 for the HSE minus is 1 times 10 to the minus 11. And I will be providing you these on quizzes and exams. All right. Let's, now remember, there's 3 sources of hydronium. Water autoionization, the contribution from the ionization in step 1, and the contribution from the ionization in step 2. Let's make our simplifying assumption so we can ignore the contribution from the autoionization of water. And let's do that test. Let's multiply Ka2 times 1,000 and see if Ka1 is bigger than that. If it is, wada bing, wada boom, we can ignore step 2's contribution of H3O plus as well. So you ready? So let's take Ka2 times 1,000. So Ka2 is 1 times 10 to the minus 11th. So that should give us 1 times 10 to the minus 8th, I believe, right? 1 times 10 to the minus 8th. Ka1 is way bigger than that. Way, 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 way bigger. Okay, so that's less than Ka1. So we can ignore the contribution from step 2. So we're going to ignore step 2. Yes! So now we're just going to worry about step 1 and treat it like a monoprotic acid. Ice table, go back, same old thing we've been doing. And the underlying assumption here is we're also ignoring the contribution from the I'm not even going to write that down, but we are ignoring the contribution of hydronium ion from the autoionization of water. You're welcome to write that down. I'd be supremely impressed on exams. But no, I'm not going to give you extra credit. You're always asking for extra credit. But if you write that down, I'd be like, yeah, thumbs up while I'm graded, but no brownie points. I should make that worth a point. But this will be worth, definitely. You've got to prove that in order to continue this problem. All right, now that we have that, let's just focus on this step right here. And step 1 for type 3 equilibrium problems is Q versus K, right? So let's calculate Q and see which way this is going to shift. Now, obviously, we're starting with this and none of these, so it's obviously going to shift right. We have no products. And it's got to shift to the right. But let's go ahead and do it. So Q for step 1, right? We're doing step 1 only, is going to be equal to the HSE minus times the hydronium ion concentration, both with coefficients of 1, so they are raised to the power of 1, over the original diprotic acid, the hydroselenic acid, raised also to the power of 1. These are going to be 0, right? If I don't give you the starting amount, we're assuming it's 0, so that will be 0 times 0. Have you seen this before? Like almost every single type 3 problem. The original H2SE was 0.098. Of course, that's going to be equal to 0, which is less than Ka1. That means this baby, Q is less than K. This is going to shift to the right, my friends. So we have proven that we can ignore step 2. So like I said, if you get to these problems and freak out on tests, just do the 2 ionization steps, write the Ka1, Ka2 values, and be done with it. And if you remember any more beyond that, continue on. So I'm going to pause this, erase this crazy board, and do another crazy board. But if you are feeling pretty confident because you've been studying these other videos, ignore the second one. Just set up the equilibrium equation for step 1. Do your ice table. We know that the reactants are going to be negative. The products are going to be positive values because it's shifting to the right. I think that's right. I'm looking in the mirror. When I see the mirror image of it. Yeah, that way. Okay, shifting that way. So these will be negative. Those will be positive. Set up your ice table in terms of X. Set up the equilibrium expression. Solve for x, making the assumption that we've got less than 5% error. Get x, figure what x relates to, see if you can get the pH for me. And then we'll do the equal, and the key is, the tough part's going to be the equilibrium concentration of the selenide ion, where we have to do some assumptions. All right, let me set up the next table for you. Let's do a nice table. Did you do it? Did you do it? Did you do it? See if you can always try to solve. If you feel confident, try to solve for these before I do, because you have the ability. In a live lecture, you couldn't do that because I'm just mowing through, right? And you're just madly trying to take notes to keep up and trying to figure out what I do later. But with these, there's a distinct advantage where you can just pause the video, you know, while you're sitting on your couch or your bed or in your backyard enjoying the hummingbirds and the sun, whatever. Pause the video and try to work it out on some scratch paper. And if you get what I get, you're going to feel pretty confident for exams. So let's punch this out. I rewrote the equilibrium equation for step 1, because remember, we're ignoring step 2. Not that it's not happening again, it's just it's so insignificant, we're not worried about the hydronium ion concentration from it. Set up your ice table. And our initial amounts, if you remember, was 0.098. molar. Water we don't worry about. That's a condensed phase. And then we started with 0 of our products. And you can just see it's shifting, right? But we proved that Q is less than K. Q was 0. So we know it's shifting to the right. So these are going to be going down, negative values of X. These will be going up, positive values of X. And because they all have stoichiometric coefficients of 1, that's not going to be true when we get to our chapter on looking at slightly soluble solids in equilibrium. We're going to have it's going to get a little more fun solving for X, because not everything's going to have a coefficient of 1. But I know I'm losing X of my original polyprotic acid. I'm gaining X of my HSE minus, and I'm gaining X of the hydronium ion concentration. These ice tables should be pretty simple now. My equilibrium concentration of my original polyprotic acid will be 0.098 minus X. And then HSE minus, the conjugate base, will be 0 plus X, or just X. The hydronium will be 0 plus X, or just X, easy peasy. Now we can set up our equilibrium expression in terms of the equilibrium values, all right? So this will be the constant, just like our Q, just Q is initial amounts and K is our equilibrium amounts. And I could have done a polyprotic base as well. You'd set it up exactly the same way. You would just be producing OH minus, the hydroxide ion, instead of hydronium ion, and we'd use KB1 instead. It's exactly the same type of problem. So let's take our products, HSE minus, times the hydronium ion concentration, both raised to the power of 1, over the original H2SE down there, also raised to the power of 1. Well, I know HSE minus is X. I know the hydronium ion is X. I know the original H2SE was 0.098 molar minus X. We're going to make that assumption that X is tiny, 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 so that we can say 0.098 minus X is just 0.098. So let's make that assumption. Let's take X times X and make it X squared up in the numerator. And let's take 0.098 minus X as just 0.098. You know what that means? We have to prove that assumption as well. So we had to prove the first assumption, that Ka1 was more than 1,000 times Ka2 to ignore the hydronium ion from the step 2 ionization of this. And now we have to prove the assumption that X is small, because if this is greater than 5% error, we'll have to use the quadratic equation. Oh no, which is doable, but this should work on exams. Ready? So let's test the assumption. Test the assumption. You can either solve for X and divide it by 0.098, multiply it by 100, and see if that's less than 5%. That would be your percent ionization, by the way. Or you can use that shortcut. You don't have to, but you can use that shortcut that I gave you. That if the molarity of the acid divided by the acid ionization constant is greater than 100, right? If it's greater than 100, then this assumption is valid. And if that was a base, you just do the molarity of the base divided by Kb. So let's equate this out. What was our molarity? 0.098 What's Ka1? What was Ka1? I have promptly forgotten. It was on the other board. Easy for you. You got your papers in front of me, but I erased my whole board. So for hydroselenic acid, that was the 1.3 times 10 to the minus 4. Yes, 1.3 times 10 to the minus 4. Good to 2 sig figs across the board. I get 753.8. 753.8. Good to 2 significant figures. I think that's greater than 100, right? So therefore, our assumption that x is small is valid. Yay! This should be pretty easy to solve for x now. So let's bring this down. I'm going to isolate the x squared, right? So x squared will be, bring the 0.098 over, will be the Ka1 times the original concentration of the hydroselenic acid. Right? So all I did is I just multiplied through by 0.098 on both sides. So I need to take the square root of both sides to get x. X will be equal to the square root of K. What was Ka1? 1.3 times 10 to the minus 4. Let's write that in there. Times the original concentration, 0.098. There we go. Not too tough, right? 2 significant digits in the concentration, 2 significant digits. That's about the most you're ever going to see in your K values. Pop those in, and I get 3.569. 3.5, good to 2 significant digits, 69 times 10 to the minus 3rd molar. No need to round that, right? I haven't asked for that. I'm not asking for x. I'm asking for the pH and the equilibrium concentrations of all species. So all we've done, we did our Q versus K, did our ice table, set up our equilibrium expression, and solved for x. Now, in the next board, let's look at what x is. And we're trying to figure out what the hydronium ion concentration is. Well, that happens to be x, right? So all you got to do is take the negative log of that, and you've got the pH. Wada bing, wada boom, you know, with all of our assumptions applied in there. And this should be less than 5% error. That's a little closer I'm happy with. So that'll probably put you in the 2 to 3% error range most likely, but it's still less than 5, so okay for this level. Maybe not, high level research or something like that, or if you're taking doing a master's or PhD graduate level course, you probably have to use the quadratic equation on this, but that's okay. Calculators do it in 2 seconds anyway. But I always make the assumption I'm not going to allow you to use the quadratic equation on quizzes and exams, because it's like you just hit some button. You don't really know what you're doing, right? It does it for you. So I want you to show that you're thinking on the exams, right, and the quizzes. So I'm going to pause it. I'm going to erase this. Do me a favor, calculate the pH and get the equilibrium concentrations of the HSE minus ion, the hydronium ion, and the selenide ion from the second ionization step. Review back on video 10 if you don't remember the wonderfully awesome trick we're going to do to get that. So let me erase this board. Did you finish it up for me? I rewrote the equilibrium equations. You don't have to because you've got them on there. But again, I wrote these up there. We're after several things. We're after the equilibrium concentration of that species, right? We're after the equilibrium concentration of the hydronium ion. And we're after the equilibrium concentration of the selenide ion. And then the pH will just be the negative log of that. So you can do them in whatever order you want. Let's go ahead and do the equilibrium concentrations first. Right? We know from our ice table, we solved for x, correct? Well, from our ice table, x was the concentration of the HSE minus and the concentration of the hydronium ion, right? They were both equal to x because we were able to assume that this coming down doesn't produce enough hydronium to impact that, and it doesn't ionize enough to drop that, right? That's such a low Ka value, that Ka2 is so small, such a small concentration that the amount that this decreases doesn't change the original HSE minus you formed in the first step. So we can just assume that HSE minus will be x, H3O plus will be X because the amount we produce here doesn't really change that amount there. The water ionization doesn't produce much. So let's write our value from X, which was 3.569 times 10 to the minus third molar. That's what was our value for X because our assumption was valid. And so that rounds to 3.6, correct? 3.6 times 10 to the minus third molar. Those assumptions, man, really makes life simple. Let's calculate the Se2 minus using a trick, and let's take the negative log of this to get the pH. So I'm going to go ahead, and since I have the hydronium ion concentration here, let's just solve for the pH. I don't care what order you do it in, but we should be able to do that now. So pH is the negative. Remember, when you pee on something, you take the negative log of it. It's the negative log of the hydronium ion concentration, which will be the negative log of 3.569 times 10 to the minus third. Two significant digits in our concentration, when we take the log of that, converts into two decimal places. So we'll get two decimal places. I get 2.4474. 2.4474. So that's going to round up to 2.45. That will be our pH, which makes sense. It is an acid, right? It should be less than 7. 2 of the 4 things done. We got, no, 3 of the 4. We only got 1 left. We got those concentrations. We got the pH. We just got to get that concentration of that selenide ion from the second ionization. Remember, it's still happening. It's just pretty minor. It's going to be a teeny, teeny, tiny value. Here's the trick. Let's set up the Ka2 expression for step 2. Ready? So from step 2, the second ionization, Ka2 will be equal to the selenide ion concentration. We have to do it because it's the only thing that has the selenide ion concentration in it, times the hydronium ion concentration over the HSE minus concentration. And if you wanted to, again, you could go ahead and set up an ice table, and you'd see these numbers would be the same and they would cancel out. But you don't have to. You can just skip it because we know from the fact that since Ka1 was greater than 1,000 times Ka2, that the hydronium ion concentration is equal to the HSE minus concentration. That's what we get from that assumption. These are both equal to X. They're going to be the same number. Therefore, those cancel out. Right? Those cancel out. Therefore, the selenide ion concentration will just be equal to the value of Ka2 from our Ka table. Sweet! So let's look up our hydroselenic acid here. There's Ka1, the 1.3 times 10 to the minus 4. There's the Ka2, 1 times 10 to the minus 11. So this will be equal to 1 times 10 to the minus 11th molar. See, that's so small. I mean, it's all pretty much insignificant, but it's not zero, my friends. Expect a problem like this on your exam. Study it, hug it, love it, know it well, and practice it, and you'll be good to go. Make sure you practice some on a base. You don't know if you're going to get a diprotic base or a diprotic acid. You rock, guys. Keep it cranking.